We love to picture giant star arcs gliding between the stars, whole cities sealed inside for generations. But almost nobody asks the brutal question: how long before the ship itself gives up? In this video, we're going to stress test the idea of a generation ship using real physics and real mission data, tearing through radiation, dust at relativistic speeds, failing reactors, fragile biospheres, software rot, and even cultural collapse. By the end, you'll see whether a ship can truly outlive the people who built it, or whether deep space inevitably turns every arc into drifting wreckage. But before we continue, please subscribe to the channel if you enjoy the video. Let's continue. Before you talk about generation ships lasting centuries, you have to look at what we've already flown, and how long those systems really survive. First, the record holders, Voyager 1 and Voyager 2. They launched in 1977 and have been operating for almost 50 years. Voyager 1 is now more than 24 billion kilometers from the Sun, around 15 billion miles. Out there, sunlight is extremely weak. Temperatures are just a few degrees above absolute zero, and the only energy they have is from their nuclear power sources. For decades, they've taken hits from tiny dust grains moving at tens of kilometers per second, and they've been exposed to a constant stream of high-energy particles, cosmic rays and solar particles. No repairs, no refueling, no replacement parts. Just hardware built in the 1970s, still running. That sounds impressive. And it is, but look at the power numbers. Their radioisotope generators started at roughly 470 watts of electrical power each. After all this time, they're down below 250 watts, about half. As the plutonium-238 decays, the heat output drops, and the electrical power follows. To keep the mission going, engineers on Earth have had to shut down instruments, turn off heaters, and cut systems, just to keep the communication and a few sensors alive. Within the next decade or so, the power will be so low that even the transmitter probably cannot stay on. The spacecraft themselves might keep drifting for millions of years, but as active, functioning systems, they are already in their final phase. That's your first hard fact. Even a simple, unmanned probe, doing almost nothing compared to a crewed ship, struggles to stay fully operational beyond one human lifetime. So if that's what happens far from Earth with no help at all, what happens closer to Earth, where we can actually send people and cargo up to fix things? Now look at Hubble and the International Space Station. They're much nearer, in low Earth orbit, around 400 kilometers up, about 250 miles. That sounds gentle compared to interstellar space, but the environment is still punishing. They circle Earth roughly every 90 minutes. That means they move in and out of sunlight 16 times per day. When they're in sunlight, outer surfaces can reach around plus 120 degrees Celsius, about plus 250 degrees Fahrenheit. In Earth's shadow, they drop to around minus 150 degrees Celsius, about minus 240 degrees Fahrenheit. That constant thermal cycling makes materials expand and contract over and over, which slowly stresses joints, bolts, and welds. There is also atomic oxygen, single oxygen atoms moving at orbital speed, which chemically attacks many materials, stripping away protective coatings and degrading polymers. Add micrometeoroids and small debris fragments hitting at around 7.8 kilometers per second, about 17,500 miles per hour, and you get a steady rate of surface damage. Radiators, handrails, insulation, everything exposed is slowly worn down. Hubble has stayed alive only because astronauts visited multiple times, swapped out gyroscopes, upgraded instruments, and replaced electronics. The ISS survives only because there is constant maintenance, constant resupply of replacement parts, food, water, and propellant. Without that support, both would already be well into serious decline, not just from one failure, but from hundreds of small failures piling up. So near Earth, with help, complex systems can last a few decades. But a generation ship will not have a cargo ship from home arriving every few months. It has to be its own Hubble servicing mission and its own ISS resupply forever. At this point you might say, but some missions went way past their design life. Doesn't that mean we can just overbuild everything and be fine? Look at the Mars rovers. Spirit and Opportunity were designed for about 90 Martian days, roughly 3 months. Opportunity ran for almost 15 Earth years. Curiosity has been active since 2012, Perseverance since 2021. They've survived intense day-night temperature swings, dust storms that block sunlight for weeks, and a thin atmosphere that provides almost no shielding from radiation. The reason they last so long is that engineers gave them big safety margins. Solar panels produced more power than needed at the start. Electronics were radiation hardened. Mechanical parts were tested for far more cycles than the mission required. When dust built up on Opportunity's panels, occasional winds cleaned them. In short, design life was conservative and reality was kind. At least for a while. But again, these rovers don't run life support. Hospitals, farms, or schools. If a wheel motor fails on a rover, you lose some mobility. If a pump fails in a ship's oxygen system, people start dying quickly. The overperformance of Mars rovers tells you that, with smart engineering, you can beat your original schedule by a factor of 10 or 20. It does not prove that a closed, crude ecosystem will just keep working for 500 years without deep structural support. So across all these missions, probes, stations, rovers, what really goes bad first? What actually limits lifespan? The pattern is clear. Structural shells, tanks, and basic metal frames can last quite a long time. What usually limits you are power systems, moving parts, and complex electronics with complex software. Batteries lose capacity with every charge and discharge. After a few thousand cycles, they hold less and less energy. Solar arrays lose 1% or 2% of efficiency per year, from radiation damage and tiny impacts. Bearings, gears, and lubricants in motors and pumps wear down, dry out, or chemically change. Valves begin to stick. Seals become brittle and start to leak. On the electronic side, radiation flips bits in memory, slowly damages semiconductors, and can cause rare but dangerous failures. Software has to be patched, reconfigured, and sometimes rewritten to bypass failed hardware. Over time, the code base becomes more complicated and harder to manage. Every workaround adds more possible failure points. A generation ship is not a small probe. It is closer to ISS plus a city plus a factory, all in one structure. If even a single orbiting telescope needs major servicing every decade or two, your ship has to carry the tools, machines, and knowledge to do that level of intervention from the inside. Continuously. On everything. So if you scale all this up with no magical new materials, how long can you keep such a ship in good shape? If you took today's best space technology, made it more robust and packed in a lot of spares, you could probably keep a large, comfortable, Earth-like generation ship running well for maybe 50 to 100 years, as long as you dedicate a huge amount of crew time to maintenance. That already means multiple generations are born and die on board. To reach several hundred years, you need more than strong hardware. You need a full repair ecosystem, recycling of metals and plastics, manufacturing of new parts, routine replacement of reactors, pumps, computers, and life support modules. You need training systems that keep producing expert engineers and technicians, generation after generation. The key lesson from all current spacecraft is simple and harsh. There is no set it and leave it in space. The true lifespan is not what the hull can survive. It is how long you can keep fixing and upgrading everything inside. So if that is already the situation just from looking at hardware, what happens when you add one more factor that never stops, that you can't turn off, and that slowly damages both people and electronics every single second? Radiation. Radiation is the one thing you can't bargain with in space. It never shuts off, and it doesn't care if you're a human or a microchip. If you want a generation ship to last more than a few decades, you have to get very serious about what those invisible particles are actually doing to you every single day. Start with the numbers we've actually measured. When NASA sent the Curiosity rover to Mars, they flew a radiation detector during the cruise. In deep space, between Earth and Mars, it saw about 0.66 millisieverts per day. Over a year, that's more than 200 millisieverts. For context, a typical chest X-ray is on the order of a fraction of a millisievert. So you're talking about the dose of hundreds of X-rays per year, just for existing in that environment. Now compare that to low Earth orbit. Astronauts on the ISS are partly shielded by Earth's magnetic field and atmosphere, even at 400 kilometers altitude. They see less than half of that Curiosity deep space dose. So when you leave the protective bubble around Earth and you're cruising between planets, the radiation level jumps up sharply. An interstellar generation ship does not live in the ISS regime. It lives in the Curiosity regime, or worse, and it lives there not for a 6-month cruise but for centuries. That's a completely different problem than the short missions we run today. So the dose is high, but how much can a human body actually take? Not just for one mission, but over entire lifetimes and across generations. Right now, space agencies set career radiation limits for astronauts. Depending on age, those limits are roughly in the range of 600 to 1,200 millisieverts total over an entire career. That's not a hard physical wall. It's a policy limit to keep cancer risk at an acceptable level, but it shows you the scale. Now compare that to the deep space number, around 200 millisieverts per year. In that environment, a single decade, just 10 years of exposure, could give someone 2,000 millisieverts if you didn't shield them. That already blows past current astronaut career limits by a factor of 2 or 3. On a 500-year mission, you're not just thinking about one crew doing one tour. You're thinking about children being conceived, born and raised in that radiation field, generation after generation. Unshielded, that is not just higher cancer risk. That is long-term genetic damage building up in the population. So for a generation ship, the target can't be we accept astronaut-style risk. The target has to be bringing the dose down into the range of natural background on Earth. That's only a few millisieverts per year, depending on where you live. If you want healthy pregnancies, normal childhoods, and normal life expectancy, you need to hit that kind of number, not 200. That leads straight to the physical question you cannot dodge. How thick does the hull really have to be to make that happen? Measurements from various missions and ground tests tell us this. If you wrap your crew in something like 10 to 20 centimeters of water, or polyethylene, you might cut the galactic cosmic ray dose by a factor of 2 or 3. That helps, but it's nowhere near enough to take you from 200 millisieverts per year down to a few millisieverts. To really push doses toward Earth-like levels, you are realistically looking at shielding layers on the order of meters, not centimeters. Water, plastic, regolith, metal, layered composites all count as water equivalent mass in different ways. But the key number is mass per area. Take a 2-meter thick shell of water around the living areas. That works out to about 2,000 kilograms per square meter of wall, because each cubic meter of water is 1,000 kilograms. And you have 2 meters of thickness. In American terms, that's over 400 pounds per square foot. So for every square meter of habitat wall, you are essentially carrying the mass of a small car. Spread that over a rotating habitat ring with, say, tens of thousands of square meters of area, and your shield mass climbs into millions of tons. That seems insane at first, but if you build the ship from asteroid or comet material in space, or you mine ice and rock at the edge of a solar system, that kind of mass is at least physically possible. It just means your design has to treat shielding as one of the main structural elements, not an afterthought. But radiation doesn't only hit people. What does this environment do to the electronics that run your life support, navigation and factories decade after decade? In high-orbit satellites and deep space probes, we already see what high-energy particles do to microchips. Particles slam into memory cells and flip bits from 0 to 1 or 1 to 0. Sometimes they cause latch-ups, where a circuit locks into a wrong state and has to be power cycled. Over time, radiation also physically damages the semiconductor material, slowly degrading performance. To survive this, satellites use radiation-hardened chips, thick shielding over critical electronics, and error-correcting memory that can detect and fix many bit flips on the fly. Even so, many commercial satellites are retired after 15 to 20 years because their electronics are no longer reliable enough, or their power systems have degraded. Now stretch that environment out to centuries. On a generation ship, the same kind of particles are constantly hitting your computers, storage drives, sensors, and control units. If you don't have strong error correction, redundant processors that can vote and cross-check each other, and the ability to physically swap damaged boards with new ones, your core software will slowly corrupt. Over 100 or 300 years, that can mean subtle bugs creeping into navigation, life support control, and industrial systems, until something fails in a way nobody expects. So you are not just shielding flesh, you are shielding the nervous system of the ship. Thick mass around crew areas, extra shielding around server rooms, and control electronics. Conservative chip designs with big features that can take more damage, and again, the ability to repair and replace everything. With all that, does radiation still put a strict time limit on how long the ship can last? Or can you push past that? If you actually give the living zone something like 2 meters of water-equivalent shielding, and you add localized extra shielding in sensitive areas, you can probably push the effective radiation dose for people down into the range of a few millisieverts per year. That is comparable to natural background on Earth. At that level, you can have normal human lifespans, and no extreme spike in genetic damage, even over many generations. Electronics will still age, materials will still slowly accumulate damage. You will still have to constantly repair, rebuild, and replace. But with good shielding, radiation itself stops being a hard ceiling, like you die after 30 years. It becomes one more slow, manageable enemy. Without that level of shielding, though, you really do get a hard limit. With something close to the Curiosity deep space dose, sustained over decades, cancer risk climbs, cardiovascular damage builds up, and child development is at serious risk. In that case, the ship very likely does not make it even 30 years as a healthy, stable society, let alone 300. So once you accept that you must wrap your city in millions of tons of shielding just to keep people and computers from being slowly cooked by particles, there's another threat that suddenly becomes just as serious. Radiation hits you from every direction. But there is something else that hits you from one direction only, head on, and it gets deadlier the faster you go. Radiation hits you from every direction, all the time. But there's another threat that hits you almost entirely from the front, and it gets worse the faster you go. That's dust and small rocks, and the data we already have tell you this is not a small problem you can ignore. Start with low Earth orbit, where we actually have hardware that's sat outside for years. The Long Duration Exposure Facility, basically a big box covered in test materials, spent nearly 6 years a few hundred kilometers up. When it was brought back and examined, engineers found thousands of tiny impact craters per square meter on exposed surfaces. Most of the projectiles were micrometeoroids, or small bits of debris, only a few micrometers across, smaller than a grain of talcum powder. Those particles were hitting at about 7.8 kilometers per second, around 17,500 miles per hour. Each one is tiny, but at that speed they punch pits into aluminum, crack coatings, and roughen up surfaces. Over just a few years, outer layers erode, radiators get pitted, paints and thermal blankets peel and flake. It's literally mechanical damage from constant tiny impacts. And remember, that's in low orbit, inside Earth's gravity well, and partly inside Earth's shield of debris and atmosphere. It's already rough there. A generation ship is not sitting comfortably in LEO. You're sending it through environments with less protection and much higher speeds. So if a few years in low orbit already scars hardware, what does the true interstellar environment look like when you start pushing to a noticeable fraction of light speed? The phrase "space is empty" is only partly true. In the local interstellar medium, the number density of gas atoms is on the order of 0.1 to 1 atom per cubic centimetre. That's very thin compared to Earth's atmosphere, but it's not zero. On top of that gas, there is dust, tiny solid particles, some smaller than a micrometer, some tens or hundreds of micrometers across. The gas mostly causes drag and heating over very long distances, but the dust is what you really care about for impacts. Even a 1 micrometer grain, if you're moving at 0.1 times the speed of light, which is about 30,000 kilometers per second, or 67 million miles per hour, carries a huge amount of kinetic energy for its size. At those speeds, that tiny particle hits like a high-velocity bullet. Models of the local dust distribution suggest that across tens of light years of travel, every square meter of frontal area on your ship will be struck by an enormous number of these tiny grains. And more importantly, by a smaller number of much larger grains in the 10 to 100 micrometer range. Those bigger ones are the real killers, because their impact energy scales both with mass and with the square of the speed. A 100 micrometer rock at 0.1 C is not just a scratch. It is an explosive event at the point of impact. So you're not flying through a clean vacuum. You're driving a huge target through a thin but deadly dust field for centuries. That means the front of your ship cannot just be a pretty nose cone. It has to be a consumable shield. We already use a version of this idea in Earth orbit, and it gives you a starting point. How do we currently protect spacecraft from small, fast projectiles? NASA and other agencies use what are called Whipple shields. The basic idea is simple. You put a thin sacrificial layer a short distance away from the main hull. When a small particle hits the first layer at high speed, it shatters into a spray of plasma and fragments, which then spread out before they reach the second layer. The energy is distributed, and the main wall survives. The ISS has multi-layer shield stacks that can stop debris a few millimeters across at around orbital speed. For low Earth orbit conditions, that works fairly well. But scale the impact speed up from about 8 kilometers per second to something like 30,000 kilometers per second at 0.1 C, and the energy per impact goes up by a factor of millions. A thin bumper is not enough anymore. For a starship moving at that kind of speed, the bumper at the front would likely have to be several meters thick, made of layers of metal, foam, water ice, or some other material that is easy to produce and replace. Over the course of a 100-year cruise, that bow shield will lose material. Impacts will vaporize small bits, crater larger chunks, and slowly erode the leading face by centimeters, maybe more, depending on dust density. Stretch that to 10,000 years, and now you are talking about meters of lost thickness. So the nose of your ship is not a one-time piece of armor. It's a consumable, ablatable structure you have to keep feeding with new material, mined, processed, and installed by your onboard industry. That sounds bad, but there's one lever you completely control here, and it changes everything: your speed. How does changing speed help you when you also care about getting anywhere in a reasonable time? The key here is that impact energy goes as the square of velocity. If you cut your cruise speed in half, say from 0.1 C down to 0.05 C, you don't just halve the impact energy, you reduce it by a factor of 4, go all the way down to 0.01 C, so about 3,000 kilometers per second, or 6.7 million miles per hour. And you reduce impact energy by a factor of 100 compared to 0.1 C. At around 0.01 C, the same dust grains are still a serious engineering problem, but they're no longer apocalyptic. Your shields can be thinner, your erosion rate slows down, and repair becomes manageable. The price you pay is time. Alpha Centauri, at about 4.3 light years away, takes a little over 40 years at 0.1 C, ignoring acceleration and deceleration. At 0.01 C, the same distance takes more than 400 years, plus extra time at the start and end of the trip for speed changes. For a crew that expects the journey to last generations, that trade-off might actually be worth it. A slower ship may have a much higher chance of survival because its environment is less violently destructive. But even at slower speeds, the nose of the ship is slowly being eaten away. So you have to ask a different question. What really decides when the hull runs out? What sets the actual limit here? If you build a thick sacrificial shield at the front, choose a modest cruise speed like 0.01 C, and commit to aggressive repair and replacement. Then simple physical erosion by dust probably does not give you a hard end date. Instead, you're in an ongoing race. On one side, you have the universe constantly throwing particles at your bow. On the other side, you have your industrial system, melting down damaged material, adding fresh mass from onboard reserves or captured comet and asteroid chunks, and rebuilding the shield in layers. If your onboard factories can replace, say, a few centimeters of shielding per century, and if your erosion rate is also only a few centimeters per century at that speed and in that dust environment, then you can, in principle, keep up. In that case, a generation ship could travel for thousands of years and still keep a solid protective front. If, however, your industry cannot keep pace, if your shield production falls behind the erosion, then the bow gradually turns into heavily cratered, thin, and structurally weak material. Cracks link up, holes open, and eventually a single larger grain can punch through and hit something critical behind it. That might not end the ship instantly, but it raises the risk with every passing century. So dust and pebbles don't necessarily say you die after 300 years. What they really say is Your survival time is exactly as long as your shield factory stays ahead of the damage curve. And that theme keeps repeating. Radiation forces you to build thick, heavy shields. Dust forces you to add a constantly renewing armoured front. Both of those push your design towards something very big, very massive, and very power-hungry, which leads directly into the next hard question. How do you keep a moving city wrapped in millions of tons of shielding, powered for centuries, without going dark? Power is the one subsystem that, if it fails hard, kills everything else in minutes. Air systems shut down, pumps stop, farms go dark, computers die. So for a generation ship, the question is simple and brutal. How do you keep megawatts of reliable power flowing, not for a mission, but for centuries? Start with the nuclear batteries we already use in deep space. Voyager's power comes from radioisotope thermoelectric generators, RTGs, using plutonium-238. That isotope has a half-life of about 87.7 years. In plain language, the heat output, and therefore the electrical power, drops by a little under 1% per year. After around 100 years, you are down to roughly half of your original power. After about 300 years, you are at roughly 1/8. For a small probe that needs only a few hundred watts, that slow fade is acceptable for a while. RTGs are great for 50 to maybe 100 years of useful performance, with no moving parts and very high reliability. But scale this to a generation ship that needs not hundreds of watts, but tens or hundreds of megawatts to run life support, farms, factories, spin habitats, and computing. To get that kind of power from RTGs alone, you would need an absurd mass of plutonium-238, far beyond current or near-future production capacity, and you would still face the same decay curve. No matter how much you launch, the power drops steadily over time. You can't fix that with maintenance, because it's the physics of radioactive decay. So RTGs are good for probes and small backup systems, but they are basically useless as a primary power source for a city-sized arc over centuries. If nuclear batteries fade out, what about the simplest power source we know? Sunlight, huge solar farms stretching across the hull. Solar power looks attractive at first, because at Earth's orbit you get about 1.3 kilowatts per square metre of sunlight. Modern panels can turn a fraction of that into usable electricity. Cover a few square kilometres in panels, and you can feed a lot of systems. The problem is sunlight intensity falls off with the square of distance from the star. At 10 astronomical units, around the distance of Saturn, the sunlight is down to about 1% of its strength at Earth, so only around 13 watts per square metre. At 100 astronomical units, you are at 1/100th of that again, essentially a dim glow. By the time you reach a few thousand astronomical units, which is still nowhere near another star, the sunlight is so weak you can barely measure it. On top of that, real panels degrade. Radiation damage and small impacts reduce their efficiency by 1% or 2% per year. Over decades, the actual output per square metre slides downward even faster than the simple distance calculation suggests. Solar is perfect for ships staying inside a solar system, especially near the star. It completely falls apart as the main power source for a true interstellar arc, because for most of the trip, you are in deep darkness with practically no incoming light. You need something that doesn't care how far you are from any sun. That points you straight at full reactors, not small RTGs, but real fission power, more like a nuclear submarine than a satellite. Can that logic scale? We already operate nuclear submarines with pressurized water reactors that can run for 25 to 30 years on one fuel load, producing tens of megawatts of thermal power, which converts to several megawatts of electricity. They do this inside a steel tube under the ocean, with high reliability, and with complex but well-understood safety systems. For a starship, you can imagine one or several reactors in the megawatt to gigawatt class. If you can refuel them, or swap cores, maybe once every few decades or every century, using fuel loaded before departure or bred on board, you can, in principle, keep fission reactors working for hundreds of years. The main limitations are not the fuel itself. Uranium and thorium, if you bring enough or breed more, can last a very long time. The limits are the hardware around the core. Pumps wear out. Turbines suffer from fatigue. Neutron radiation slowly damages the reactor vessel and the internal structures, a process called embrittlement. Sensors drift. Control electronics age. To keep fission working for centuries, your ship must be able to fabricate and replace everything around the core. Pumps, pipes, heat exchangers, control rods, shielding blocks, power electronics. That is a heavy industrial load, but unlike plutonium-238 decay, it is something you can fight with maintenance. Still, fission is basically stretching today's tech. Many generation ship concepts quietly jump to something more advanced, fusion, or to external beaming. Does that really help your long-term power budget? If practical fusion becomes available, especially reactions like deuterium, helium-3, the game changes. Deuterium, a heavy form of hydrogen, is reasonably abundant. About 1 atom in every 6,000 hydrogen atoms in Earth's oceans, and in gas giants and icy bodies. That means huge amounts of potential fuel in almost any planetary system. Fusion fuel has an energy density much higher than fission. A single kilogram of fusion fuel can release vastly more energy than a kilogram of uranium in a fission reactor. For a starship, that means you could, in theory, launch with a compact supply of fusion fuel and top up from gas giants or icy bodies at your starting system or destination. Reactors could be smaller for the same power, and you are not stuck with long-lived radioactive waste in the same way. But the same reality applies. The fusion core is only part of the system. You still need pumps, magnets, structural supports, heat rejection systems, and very capable control electronics. Those all age. Even with fusion, you need a heavy industrial base on board to keep the reactors going. Beamed power, lasers or microwaves pushing light sails, is another idea. Ground or orbital stations near your home star. Fire powerful beams at a sail attached to your ship, accelerating it without you carrying all the reaction mass. This helps a lot for the acceleration phase and maybe the first segment of the journey. But once you are far from the origin and out of line of sight, those beams can no longer reach you unless you build an entire network of relay stations across multiple systems, which is far beyond any first mission. Also, beamed power for propulsion does nothing for your life support and city systems centuries into the trip, unless the beams are still aligned and still operating, and you have giant receivers to catch them. For a truly independent generation ship, you cannot count on a star-spanning power grid that never fails. You need internal power. So when you put all this together, does power put a hard limit on how long the ship can survive? Or can you push past that if you design correctly? If you build reactors like we build submarines today, sealed units with fixed cores and limited spare parts, you might get 30, 40, maybe 50 or 60 years of solid, high reliability power before aging and where force major overhauls. On Earth, you would retire the plant or shut the submarine down at that point. A generation ship does not have that option. To reach 500 years or 1,000 years, the reactors themselves have to become part of a larger industrial ecosystem. They cannot be sealed boxes, they have to be rebuildable machines. Your crew and your robots must be able to open them, swap internals, replace entire coolant loops, build new turbines and generators from raw metals, and install new control systems many times over. If you have that, and if you either launch with enough fissile material or can use fusion fuel collected from planetary systems, then power stops being the first thing that kills you. It becomes one more demanding, continuous project. If you do not have that, if you launch with a few high-tech reactors that nobody on board can truly rebuild, then your real mission lifetime is the lifetime of your power plant. When that ends, the ship slowly goes dark, and that likely happens in under a century. So power is not just an engineering detail. It forces you to build a full civilization in a can. Fuel refining, heavy industry, high-end manufacturing, and expert knowledge passed down for generations. And even if you solve that and keep the lights and pumps on for hundreds of years, there is another loop you cannot afford to lose for even a few days. The loop that keeps your air breathable and your water drinkable. If power is the heartbeat of a generation ship, then the air and water loop is its lungs. And there is no safe way to shut your lungs off. Not for an hour, not for a minute. So the question is, how close are we to a life support system that can actually run forever, without Earth constantly bailing it out? Right now, the closest thing we have is the International Space Station. On the ISS, roughly 90% of the water is recycled. Urine, sweat, and moisture from the air all go into treatment systems, get cleaned, and come back as drinking water. Oxygen mainly comes from electrolysis, splitting water into hydrogen and oxygen, plus backup oxygen candles that release O2 in emergencies. Carbon dioxide is pulled out of the air using chemical scrubbers like lithium hydroxide canisters and more advanced regenerative systems. On paper, that sounds like a closed loop, but here's the catch. The molecules are recycled, the hardware is not. Filters saturate, sorbent beds are used up, pumps and valves age, sensors drift, and all of that is fixed by flying up new parts, new cartridges, and new chemicals from Earth. The system has been running for more than 2 decades, but only because there's a steady stream of cargo ships feeding it. So the ISS proves you can close the loop on water and air pretty tightly. But it also proves something else. With today's tech, the loop is tight on molecules and leaky on hardware. For a generation ship, nobody is sending up a box of spare filters every 6 months. You have to manufacture everything yourself. So what are you actually managing? In raw physical terms, when you say air and water for 1,000 people. Per person, you want on the order of 20 to 30 kilograms of water in active circulation for drinking and hygiene, plus a lot more locked-in pipes, tanks, humid air, and especially in plants and soil or nutrient solutions. Realistically, for 1,000 people, you're dealing with tens of thousands of kilograms of water, tens of tons, moving through different parts of the system. The air is also a large but finite inventory, mainly nitrogen and oxygen, with tiny amounts of carbon dioxide and trace gases. Every time there's a leak, every time someone vents something by mistake, a tiny bit of that inventory is lost to space. If your recycling is 99% efficient, that sounds great, but it still means 1% is lost each cycle through the system. Over a few years, maybe you can tolerate that. Over 100 years, that kind of continuing loss is catastrophic, unless you are absolutely ruthless about capturing and reusing every molecule that ends up in waste streams, broken equipment, or even structural materials. So you need a loop that is not just efficient in chemistry, but efficient in total mass accounting. You need to know down to the kilogram where your water and your main gases are at all times, and you need to be able to pull them back out of almost anything. Scrap plastic, corroded metal, sewage sludge, dead plants. That leads to the next step. Instead of doing everything with tanks and chemicals, can you make living organisms do most of the work for you? There have been real experiments in that direction. In Russia, the BIOS-3 experiments locked small crews in sealed habitats supported by plant-based life support, using wheat, vegetables, and algae to regenerate oxygen and process waste. They managed to support 3 people for months at a time. ESA's Melissa project in Europe is another example. A loop of algae, bacteria, and higher plants cleaning water, recycling nutrients, and making food. These systems showed that, under controlled conditions, crops in artificial lighting can reach very high yields, tens of kilograms of edible biomass per square metre per year. Scale that up. To fully cover both oxygen and food for a person, you might dedicate somewhere around 50 to 100 square metres of growing area, depending on crop choice, technology, and diet. For 1,000 people, that's 50,000 to 100,000 square metres of farms, 5 to 10 hectares, roughly 10 to 25 acres, spread across your ship in greenhouses, racks and bioreactors. Those plants are not just food. They are also your oxygen generators, your carbon sinks, and your biological filters. On a generation ship, farms aren't optional add-ons. They are core life support modules. But as soon as you rely on living systems, you inherit a new class of problems. Hardware fails in predictable ways. Biology fails in messy ways. What can actually go wrong in a closed, plant-based life support loop stretched over centuries? Bioreactors and plant ecosystems can crash. If one microbe gets a growth advantage in a reactor, it can suddenly dominate and throw the whole loop out of balance. A fungus can attack a major crop species. An insect pest can hitch a ride and thrive in the artificial environment. A trace contaminant maybe a metal or an organic solvent, can slowly build up in the water loop until it starts poisoning roots or beneficial microbes. We already see hints of this on the ISS. Wherever you have moisture and human presence, you get biofilms, layers of mold and bacteria, on seals, behind panels, inside plumbing. Crews have to constantly clean and disinfect to keep them under control. Now extend that reality to hundreds of years. Your life support isn't a neat static machine. It's a dynamic biosphere that needs constant monitoring and farm-level management. You need people who are both engineers and farmers and microbiologists. You need test beds where you can trial new strains of crops or microbes without risking the main loop. And you need the ability to completely drain, sterilize, and restart sections of the system when they get out of control. So even if you manage the day-to-day, there's a deeper question under all of this. Can a small, closed biosphere stay stable for centuries, or does it slowly drift out of balance in ways you can't easily predict? Earth's biosphere has been stable enough for billions of years because it is huge and has massive buffers, deep oceans, a thick atmosphere, plate tectonics recycling chemicals over millions of years. Your ship does not have any of that. It has maybe a few million kilograms of total biological material, in a metal shell a few hundred meters across. Data from sealed habitat experiments on Earth, like Biosphere 2 in Arizona, show how tricky this is. In Biosphere 2, oxygen levels drifted down unexpectedly, carbon dioxide swung around, and soil chemistry changed in ways the designers did not fully anticipate. These shifts happened over just a few years in a structure still close to Earth, with backup help available. On a generation ship, similar drifts can happen over decades. Nitrogen might slowly get locked into long-lived compounds. Carbon might get trapped in plastics or structural materials. Trace nutrients like iron, zinc, or phosphorus can be pulled out of circulation and end up somewhere you can't easily access. The only way a ship's biosphere has a shot at surviving centuries is if you treat it like a giant ongoing science experiment. You track gas levels, nutrient flows, and microbial populations in detail. You maintain massive seed banks and microbe libraries for many crops and support species. You keep the genetic diversity high enough that you can swap in new varieties when old ones fail. And critically, you keep the capability to tear down and rebuild entire parts of the nitrogen cycle or carbon cycle if they drift too far. That means the real life support system on a generation ship is not just hardware or just plants. It's hardware plus biology plus continuous human attention. And that continuous attention is not something you can automate away completely. It needs trained people, generation after generation, who understand the loops deeply enough to fix them when they start to slide. So at this point, you're not just running air and water systems, you're running a miniature planet inside metal walls. And that leads straight into another hard limit. If your farms and food systems can't keep up, then no matter how perfect your oxygen recyclers are, your ship's lifespan is just until the last pantry runs dry. Food is where all the nice talk about closed loops hits hard reality. Air and water recycling matter, but if your calories run out, the mission just stops. So how much food does a 1,000-person ship actually need? And what does that turn your spaceship into? Start with the basic math. A typical adult needs around 2,000 to 2,500 kilocalories per day. For 1,000 people, that's 2 to 2.5 million kilocalories every single day. Over a year, that adds up to hundreds of millions of kilocalories, which is roughly what you'd get from 800 to 1,000 tons of grain if you only grew something like wheat. Now look at realistic yields. Intensive hydroponic or vertical farming on Earth can hit around 30 to 50 kilograms of leafy greens per square meter per year, and about 10 to 20 kilograms per square meter per year for grains or calorie-dense staples. That sounds high, but remember, people don't just eat lettuce and rice cakes, and you need buffer space, crop rotation, and redundancy. Once you factor all of that in, you end up needing at least a few square kilometers of growing area to feed 1,000 people properly, not just at starvation level. That's millions of square meters of racks, trays, lights, pumps, and pipes wrapped around your ship's core or inside big rotating rings. At that point, the ship is basically a farm complex that happens to move through space. But all of that assumes plants behave the way they do on Earth. Do we actually know that they can deliver those kinds of yields in space for decades? We've already done small-scale space agriculture. On the ISS, astronauts have grown lettuce, zinnias, dwarf wheat, and other plants in microgravity under LED lights with nutrient solutions instead of soil. The results are clear. Plants can grow, but it's not plug and play. In microgravity, roots don't know which way down is because there is no G. Water doesn't drain the same way. It tends to cling and form blobs. That can suffocate roots or leave them dry unless you carefully control flow. Pollination can't rely on wind or insects unless you deliberately introduce and manage them. Even basic things like gas exchange around leaves change when convection behaves differently. Yields in these experiments are usually lower and more variable than on Earth. Things work, but they're touchy. For a generation ship, you probably don't want to run your farms in microgravity at all. You want rotating habitats that simulate 1G, or maybe a bit lower, so water, soil, and pollen behave more like they do on Earth. Even then, you're not just growing a few trays of salad for fun. You have to build and manage entire agricultural ecosystems that can handle equipment failures, weird plant diseases, and long-term drift. And calories are one thing, but protein is another. Where does the ship get its meat, or the equivalent, without wasting huge amounts of space and energy on cows and chickens? Protein is expensive in terms of energy and feed. Traditional livestock like cows and pigs are horribly inefficient for a closed ship. They eat huge amounts, produce a lot of waste heat and waste products, and need a lot of space. You can't afford that. Instead, you look at systems that turn plant byproducts and waste into protein much more directly. Aquaponics uses fish and plants together. Fish waste feeds the plants. Plants clean the water. People eat both. Insect farms take in low-grade plant matter and spit out high-protein biomass in the form of crickets, mealworms, or other species. These animals convert feed to edible protein far more efficiently than cows do. Then there are microbial protein reactors. On Earth today, there are commercial systems that grow bacteria or fungi in tanks, feeding them hydrogen, methane, or other simple molecules, and producing several tons of edible biomass per year in something the size of a shipping container. On a ship, a row of those tanks could be your meat factory, turning waste streams and simple feedstocks into protein powder, meat substitutes, or ingredients for processed foods. Think of it as a steel-farmed cow that doesn't need fields or sunshine. All of that only works if the nutrients that feed the whole system stay in circulation. If key elements slowly leak out of the loop, your farms hit a hard wall. So what exactly do you have to keep track of, down to the atom? Plants don't just need nitrogen, phosphorus, and potassium. They also need a long list of trace elements: iron, zinc, copper, molybdenum, manganese, and more. These are required in tiny amounts, but if you run out, yields crash or plants fail outright. Over decades, these elements get locked into long-lived materials. Some end up in plastics, electronics, or corroded metal. Some go into human bodies, and then into waste streams that are not perfectly recycled. If any fraction of that ends up vented or trapped in inaccessible forms, your available nutrient pool shrinks. We've already seen how side effects can surprise you. In the Biosphere 2 experiment on Earth, oxygen levels dropped and carbon dioxide behaved unexpectedly, in part because the concrete structure itself absorbed CO2. The building materials changed the carbon cycle in ways designers hadn't fully predicted. On a ship, similar chemistry can unfold slowly over decades. Alloys might bind up trace metals. New construction could soak up carbon or nitrogen. That means you need very precise inventories of key elements, and you need ways to pull them back out of scrap, dirt, and even the hull when necessary. So in the end, farming doesn't just set your menu, it can set your maximum mission length. How hard a limit is that? If your agricultural system needs fertilizer shipments, mineral supplements, and new seed stocks from Earth every few years, your ship's true lifespan is simple. It lasts until the last resupply and a bit beyond. Then it starves. That might be a few decades, maybe a century at most. If instead you can close nutrient cycles to better than 99.9%, recover trace elements from waste and scrap, and maintain huge seed and gene banks for hundreds of plant and microbe species, then farming stops being the first thing that kills you. At that point, your survival horizon slides toward other limits. whether your machines can keep running, whether your knowledge survives, whether your society stays stable. And that brings up another piece that quietly underpins all of this. All these farms, tanks, pipes, and rotating rings are bolted into something. If the bones of the ship itself start to crack and creep over centuries, it doesn't matter how good your farms are. So how long do the actual materials, the beams and shells holding this whole artificial planet together, really last before the structure itself becomes the failure point? Every life support system, every farm, every reactor you put on a generation ship is mounted on something solid, and if that something fails, it does not matter how perfect the rest is. So you have to ask, not just how strong is this on day one, but what happens to the bones of the ship after hundreds, even thousands of years? Right now, modern spacecraft are built from a fairly standard set of materials: aluminum alloys, titanium, carbon fiber composite garnets, and advanced steels. The pressure modules on the ISS are mostly aluminum, for example. These materials are strong, light, and well understood. In lab tests, you can make them survive millions of stress cycles before cracks form, as long as you keep the loads within safe limits. Look at airliners on Earth. They're also mainly aluminum, and they're typically designed for a service life of maybe 20 to 30 years, with something like 50,000 to 100,000 takeoff and landing cycles. After that, metal fatigue becomes too risky, and you retire the plane or do an expensive life extension overhaul. Your generation ship is not a 30-year machine, and it's not doing just 100,000 cycles. Its rotating habitats, its load-bearing beams, its joints might go through millions of cycles of stress over centuries. That is already outside the normal design envelope for most of our current structures. So material choice is part of it, but long-term behaviour is where things get serious. In low Earth orbit, the ISS and other satellites see brutal thermal cycling every 90 minutes, flipping between minus 150 degrees Celsius and plus 120 degrees Celsius, between roughly minus 240 and plus 250 degrees Fahrenheit. That constant heating and cooling drives expansion and contraction over and over, which is a major source of fatigue. In deep interstellar space, the situation is different, but not easy. The outside is very cold, just a few degrees above absolute zero. Inside, you keep your habitats at something like room temperature, maybe 20 to 25 degrees Celsius, around 70 to 75 Fahrenheit. You can design the structure so that most of it stays at relatively stable temperatures, but any rotating ring, any structure near radiators, any system that powers up and down, will still see its own thermal cycles. Over centuries, even tiny mismatches in how different materials expand and contract start to matter. If you bolt a carbon fiber panel to an aluminum frame and they respond differently to temperature changes, the joint is under constant microstress. That slowly loosens bolts, opens hairline cracks and delaminates composites. The effect in any one year is small, but over 500 years it adds up. Then there are the slow processes that don't look dramatic but quietly reshape the structure anyway. Metals under constant load creep. They deform slightly over time, even at moderate temperatures. A beam holding up a rotating habitat ring might slowly sag or shift a tiny amount every decade. Over a few centuries, alignment changes, stress redistributes, and connections that were safe can become overloaded. Outgassing is another slow killer. Many plastics, adhesives, and composites contain trapped volatile molecules. In vacuum, those volatiles slowly evaporate and leave. That can weaken bonds, change material properties, and cause subtle warping. In low Earth orbit, atomic oxygen chews up polymers and coatings. In deep space, you lose the atomic oxygen, but you gain constant radiation, breaking chemical bonds in plastics and composites directly. Again, the structure doesn't sit there, it ages. So the bones of the ship will not remain as built forever. They will drift, creep, crack, and slowly degrade. The only way that doesn't eventually kill you is if inspection and repair are built into the very culture of the ship. That raises the question, what does maintenance actually look like when your vehicle is the size of a small town and expected to run for 500 years? On Earth, you can look at how we keep critical structures alive. Aircraft undergo regular, detailed inspections where technicians look for cracks around rivets, measure fatigue in key areas, and replace whole sections when needed. Bridges get ultrasonic scans of steel members, visual checks, stress tests. Nuclear power plants have intense inspection programs for reactor vessels, piping, and containment. A 500-year generation ship needs something like that, but scaled up to an entire city in space. Every joint, every weld, every major beam needs a scan schedule. You can't rely only on human eyes and handheld tools. The surface area is too large, and many parts are external, in vacuum. So you probably fill the structure with robotic crawlers, drones that move along rails or cables, or small autonomous bots that can walk or fly in microgravity. They carry non-destructive evaluation gear, ultrasound probes, X-ray, or gamma imagers, laser scanners. Their whole job is to patrol, record data, and flag every hairline crack and corrosion patch. When they find something out of spec, that's where your onboard factory comes in. You need to be able to print or forge replacement beams, brackets, and panels, not in kilograms, but in tens or hundreds of tons over the years. You cut out a damaged piece, brace the area, install a new piece, repressurize, going. That kind of heavy structural surgery is not a rare emergency on a 500-year ship. It's routine work. Given enough inspection and repair, how long can the basic skeleton of the ship last? Here, the news is actually better than for many other systems. On Earth, some steel bridges have been in service for over a century, with proper maintenance. Historical stone cathedrals have stood for many hundreds of years, even over 1,000 in some cases. In terms of raw material endurance, simple metals and well-designed composites can last a very long time, especially if you keep temperatures moderate and avoid corrosive environments. In vacuum, with good thermal control, no weather, no salt, no biological growth on the outside, your structural materials can, in principle, last thousands of years, as long as you keep catching and fixing the slow damage. You will need to replace certain high-stress parts occasionally, but the core hull and main rings are not doomed to fall apart after some fixed number of years. The real limit is not the material itself, it's your discipline. If you keep up the inspections, keep training people and building bots that know how to do repairs, and keep your industrial base able to produce big structural components, then the bones of the ship can outlive multiple civilizations on Earth. If, however, you let maintenance slip for a century, if you cut back inspection to save effort, or if your factory capability decays, cracks and creep don't stop just because you stopped looking. They keep growing silently until at some point a rotating ring goes out of balance, a pressure hull ruptures, or a support truss fails in a way you can't easily contain. So the structure itself is both your biggest strength and a hidden long-term threat. It can last for millennia with care, or quietly turn into a floating ruin if care fades. And that leads straight to the next brutal question. Who is actually doing all this care, all this scanning, all this manufacturing, year after year? Human crew with wrenches, or swarms of robots, or both? And what happens if that onboard industrial machine ever slows down? You've seen how the ship's bones only stay safe if someone is constantly checking and fixing them. So the next hard question is, who actually does all that work day after day? For centuries. Because right now, just keeping a small station running already eats an enormous amount of human time. On the ISS, a big chunk of astronaut hours is just maintenance. We're talking hundreds of crew hours per month spent swapping filters, replacing pumps, updating software, troubleshooting alarms, cleaning out valves and doing inspections. That's with a crew of around 7 people, in a volume much smaller than a generation ship, and with regular cargo ships bringing fresh parts and tools. Scale that to a flying city of 1,000 people. Life support alone explodes in complexity. More air handlers, more water processors, more toilets, more sensors. Then add multiple reactors, farms covering square kilometers, rotating habitats with big bearings, giant radiators, robot bays, drones, vehicles inside the ship. If you scale maintenance roughly with size and complexity, you're looking at a society where a big fraction of the adult population is doing ship work most of the time. In a medieval town, half the people had to farm just to keep everyone fed. On a generation ship, a similar fraction will be mechanics, electricians, reactor techs, farmers and inspectors, simply to keep the machinery and the biosphere functioning. There is no set and forget class of citizens who can ignore the ship. Everyone depends on that work every day, so you need help that doesn't get bored or tired, which pushes you straight to robots. But what can robots actually handle in real space operations today? And how far do they have to go for this to work? Right now, we already use robotics in orbit and on other planets. The ISS has robotic arms that move cargo, assist astronauts and capture visiting spacecraft. Small free-flying helpers like Astrobee can navigate inside the station, carry cameras and sensors, and assist with inspections. Mars rovers are full robotic field geologists, driving autonomously over rough terrain and making some decisions on their own. Autonomous docking, basic navigation, and fault detection systems are pretty mature. Spacecraft can already detect some problems, switch to backup systems and call home. But full autonomy in complex repair work is not there yet. On the ISS, any serious repair still involves human hands, guided by human judgment. For a millennia-scale ship, you need much more than arms that can grab things. You need robot machinists that can take raw metal, mill it, drill it, and finish it. Robot welders that can work in vacuum on the hull, laying down precise beads in awkward places. Robots that can cut out damaged plating, fit new pieces, seal pressure vessels and test them, all with minimal human micromanagement. Humans will still be involved, but the goal is to have robots do the repetitive, hazardous jobs. Crawling over the external truss at 3 a.m, scanning for cracks, scraping off corrosion, tightening bolts, hauling shield blocks. That raises the next question. Even if robots can do the work, where do the parts they install actually come from? The answer is that your ship must be a factory, not just a vehicle. And that factory must be able to build almost everything it needs, from itself. We've already taken first steps. The ISS has flown small 3D printers that can manufacture simple plastic tools and test parts. On Earth, metal additive manufacturing is used for complex rocket engine parts, with high strength and complex internal channels. These are early hints of a capability that a generation ship has to push to the extreme. On board, you need to be able to take scrap metal from old structures, melt it, refine it, adjust the alloy, and then cast or print it into new beams, brackets, and pipes. You need to produce pressure-rated tanks, housings for pumps, parts for airlocks, and frames for rotating habitats. You need to make circuit boards, connectors, and mechanical components for robots themselves. Even electronics, which are usually the most fragile part of the supply chain, have to be at least partly manufacturable on the ship. That means not bleeding-edge, ultra-fine chips that require entire terrestrial fabs, but simpler, larger feature-size designs that can be built with a compact, hardened fabrication line. You might import the very first set of tools and master masks, but after that you have to keep them running and repair them, maybe for centuries. If you can't fabricate at least 99% of your spare parts from onboard feedstock, recycled scrap, stored raw materials, harvested asteroid or comet mass, then your lifespan is limited by whatever you launched with. Eventually, some crucial, irreplaceable component fails, and there is no way to build a new one. That is a hard stop. When you think about what it takes to build something as simple as a smartphone today, the scale of the challenge becomes obvious. A phone depends on a whole planet's industry, rare earth metals mined in one place, silicon fabs in another, glass from somewhere else, specialized chemicals from multiple countries, precision optics, multi-layer printed circuit boards, packaging, software designed by thousands of people. Your ship has to compress that entire industrial tree into a few cubic kilometers of habitat and factory space. You don't get to call a supplier on Earth when you're short on a specific kind of epoxy or a rare dopant. That means you have to be very careful about which technologies you rely on. Ultra-optimized, tiny, delicate devices are hard to reproduce. Simpler, more modular, more robust designs are easier. Over time, your ship might favor electronics with larger features and lower integration, because they are easier to bake in your own ovens and easier to debug. Instead of chasing the latest nanometer-scale chips, you might accept bulkier, slower computers that you can actually rebuild with the tools you have. Optics might follow the same path. Fewer exotic coatings, more rugged designs you can polish and assemble in your own workshops. Software stacks might be kept deliberately simple and well documented, so new generations can understand and rebuild them instead of inheriting opaque black boxes. All of this leads to one blunt conclusion. The true lifespan of the ship is largely the lifespan of its factory. If your onboard industrial base can keep refreshing every critical subsystem, reactors, pumps, farms, computers, plumbing, habitat shells, then the main limits become long-term things, like the slow loss of some elements, and whether your society holds together. In that case, the ship's hardware could, in theory, run for thousands of years, as long as your industrial and educational systems stay intact. If the factory starts to fail, if key machine tools wear out and can't be replaced, if you lose the ability to make high-grade alloys or precision components, then your countdown begins. Systems will still run for a while on inertia and remaining spares, but complexity will start to collapse. You'll patch instead of replace, downgrade instead of repair properly, and slowly your starship shifts from a functioning city to a decaying shell. Data from current missions are clear. On the ISS, on satellites, on probes, maintenance dominates the long-term picture. It's not a side task. It is the main storyline. A generation ship is just that logic extended to the extreme. It survives exactly as long as its moving city factory can keep rebuilding itself. And even if you solve that, even if you nail down reactors, farms, hulls and robots, you still have one more category to deal with. The cargo that doesn't behave like a machine at all. Human bodies and human biology stuck in transit for centuries. How long can people themselves stay healthy in an artificial environment before their own biology becomes the weak link? Hardware can, in theory, run forever. Human bodies can't. And that mismatch is a huge problem for a generation ship. You're not just sending metal and chips into deep space. You're sending skeletons, hearts, immune systems, and unborn children. And all of that has limits that engineering alone can't erase. Start with the most basic thing, gravity. In microgravity, astronauts lose bone density at rates up to 1 to 2% per month if they don't do anything about it. With very intense daily exercise, they can slow that loss a lot, but they usually don't get it down to zero. Muscle also shrinks, balance systems get weird, the heart doesn't have to work as hard, and it all adapts to a weightless world. On a 6-month ISS mission, or even a 1-year mission, that's barely manageable. You rehab when you come home, you get your strength back over months. Stretch that over a 5-year cruise, and the strain on the body gets serious. Stretch it over generations, kids born and raised with no 1G at all, and it stops being manageable. You get grandchildren with skeletons and circulatory systems tuned for 0G, who might simply be too fragile to ever stand or walk on a planet. That's why nearly every serious generation ship design throws pure microgravity out the window. A long-term crew in deep space basically needs artificial gravity, not as a nice extra, but as a requirement, if you want anyone on board to stay healthy enough to land somewhere at the end. The standard way to get that is rotation, but rotation comes with its own hard engineering numbers. How big does your spinning habitat actually have to be to give you something like Earth normal gravity without making everyone sick? To simulate roughly 1G with a spin rate around 2 revolutions per minute, you need a radius of about 224 meters, so your habitat ring is about 450 meters across, roughly the length of 4 football fields end-to-end or a 70-story skyscraper laid on its side. If you want people to feel less Coriolis effect, less weird motion when they move their heads, you might spin slower, say 1 revolution per minute. Then you need almost 900 meters of radius, close to a kilometer, more than half a mile across. Structures that big have to be precisely balanced. If mass shifts, say a big crowd moves to one side for an event, or you add a new water tank somewhere, you change the mass distribution and the ring can start to wobble. Bearings have to handle constant load. Connection arms to the rest of the ship have to carry huge forces. Over centuries, that's a lot of stress cycling. But the payoff is critical. A rotating habitat that gives you 1G, gives bones the loading that they evolved for, keeps blood circulation closer to normal, and helps organs stay where they belong. You can raise kids in that environment and expect them to grow with Earth-like posture, strength, and balance, instead of fragile 0G bodies. Even with artificial gravity, there's still the radiation side of biology. Radiation doesn't just hit electronics, it hits cells, DNA, blood vessels. Over a lifetime, and especially over multiple generations, that damage adds up. What does that do to a population that never goes home? Medical data from astronauts and radiation-exposed workers on Earth show clear trends. Higher doses of ionizing radiation increase the risk of certain cancers, increase cataract formation in the eyes, and may raise risks for heart and blood vessel disease. The mechanism is simple. High-energy particles break DNA strands and damage cellular structures. If repair fails or goes wrong, cells may die, or worse, they may survive with mutations that lead to cancer or heritable defects. For a generation ship, the target dose can't just be low enough that you probably won't get cancer before retirement. You're designing for people who will live their entire lives in this radiation field, and who will have children there. You want cumulative doses of no more than a few tens of millisieverts per year, at most ideally in the range of natural background levels on Earth, which are often just a couple of millisieverts per year. To hit that, you need thick shielding around living zones, storm shelters with extra mass for solar flare events, and probably specially protected child zones for pregnant people and young children, where shielding is even heavier and monitoring is tighter. Without that, long-term radiation slowly undercuts your society's health, generation after generation, no matter how good the rest of your engineering is. Then there's another part of biology that people often forget until it goes wrong: the microbiome and the pathogens that share the ship with you. You are not just sending humans, you are sending entire ecosystems of microbes. Your gut microbiome alone, the trillions of bacteria living in your digestive system, plays a huge role in digestion, immune function, even mood. It is sensitive to diet, antibiotics, stress, and environment. In a closed ship, with a very consistent diet, limited outside inputs, and lots of recycled air and water, your microbiomes will drift, for better or worse. At the same time, the ship itself is a perfect environment for the wrong microbes to thrive. High density, indoor air, many surfaces, constant human presence. Hospitals on Earth already struggle with infections that evolve and spread in closed medical environments. A generation ship is basically a permanent, closed, hospital-like habitat, where any new strain that finds a niche can spread to most of the population quickly. We already see this in small ways on the ISS. Bacterial and fungal colonies adapt fast to microgravity and radiation. Biofilms form on damp surfaces and in corners that don't get cleaned enough. Over decades and centuries, you don't just have some bugs, you have evolving onboard ecosystems that co-evolve with your systems and your crew. Sometimes they help, sometimes they turn hostile. That means constant hygiene work, constant monitoring, and smart design. Smooth, cleanable surfaces, air systems that don't let pockets of stale, moist air form, strict rules for medical isolation when new pathogens show up, and maybe deliberate control of microbiomes through probiotics and engineered microbes. Taken together, gravity, radiation, and microbes tell you this: human bodies can cope with a lot, but only if you give them a very carefully controlled environment. The next layer of the problem is even bigger though. Individual bodies age out in under a century. A generation ship is betting not on one set of bodies, but on a whole chain of births and deaths. So what ultimately sets the biological lifespan of the mission itself as a living population? On an individual level, humans top out around 80 to 100 years. A few outliers reach a bit more, but that's about it. On a 500-year voyage, your original crew is dead long before the halfway point. Their children, grandchildren, great-grandchildren live, age, and die on the ship. At any given time, you have babies, teenagers, working-age adults, and elders, all depending on the life support system and on each other. The mission's biological survival window is not set by a single hard physical wall, like after 500 years DNA stops working. Instead, it's defined by whether you can keep average health good enough, birth rates high enough, and childhood development stable enough over many generations. If chronic diseases slowly rise because of low-level toxins or radiation, if subtle nutritional deficits creep in because your farming isn't perfect, if fertility drops due to stress, environment, or genetic issues, then your effective biological clock is ticking down. Even if the hardware looks fine, there is no sharp no more after X years rule from physics, but there are thousands of slow failure paths that can lead to a population that is smaller, sicker, and less fertile with each passing century. All of that means that the biology of a generation ship is not just about keeping people alive today. It's about keeping a population healthy enough that, in 10 or 15 generations, there are still enough strong, fertile, mentally stable humans on board to run reactors, fix hulls, raise children, and maybe one day walk out under a real sky. And once you start thinking in terms of generations, you run into a different kind of limit, one that doesn't show up in engineering drawings. The math of how many people you need, how genes mix, how birth rates change, and how a small, closed human population can quietly drift into a dead end, even if every machine on the ship is still running. Even if everyone on the ship is healthy right now, there's a deeper problem hiding in the background. Do you actually have enough people? With enough genetic variety to stay healthy for hundreds of years without Earth feeding new genes into the pool? The first question is blunt. How many people do you really need on board? Computer models of small closed human populations suggest that you can, in theory, squeeze by with a few hundred people. Some studies quote minimums in the range of 160 to 500 individuals, assuming perfect planning, no accidents, and careful pairing rules. Other analyses say that's way too optimistic, and you really want thousands of people. Real-world history backs up the cautious view. Isolated human communities on islands or in remote valleys, founded by a small number of people, often show genetic bottlenecks. Certain inherited diseases become common, and you see distinctive, sometimes harmful traits appear at high frequency. That's with occasional contact and some new genes still sneaking in. A generation ship won't have that luxury. So yes, maybe a few hundred is the hard mathematical minimum, but if you want a safety margin, you probably want a population in the thousands, not the low hundreds. But even if you start with a big crew, genes don't just sit still. Every generation adds new mutations, and how you handle that in a sealed environment decides whether your gene pool gets stronger or weaker over time. Each person is born with dozens of new mutations compared to their parents. Most are neutral, a few are beneficial, and some are harmful. In a large mixed population, the bad ones are usually kept under control because they are rare and spread out, and selection slowly filters them. In a small isolated group, harmful mutations can build up because the same families keep intermarrying, and chance plays a bigger role in which traits survive. Over 20 to 30 generations, which is roughly 500 to 700 years, if you assume about 25 to 30 years per generation, a ship with only a couple hundred people could see a rising mutational load. That can show up as higher rates of infertility, more birth defects, weaker immune systems, or lower resilience to disease and stress. None of this happens overnight. It's a slow drift that only becomes obvious after many lifetimes. To push back on that, a generation ship has to treat genetics like life support. Genetic screening for heritable diseases becomes normal. You might limit certain pairings or encourage others. You may need detailed family planning rules, tracking who can have kids with whom, not out of social control for its own sake, but because the math of small populations leaves you no choice. It's not a comfortable topic, but ignoring it doesn't make the risk go away. On top of that, your population size itself is constantly changing. It's not enough to say we launch with 1,000 people. How many are born? How many die? And at what ages? All change the stability of the mission. If you assume an average generation time of 30 years, then a 300-year trip spans 10 generations. You cannot treat the crew as a static group. If, for a few generations, birth rates drop below the simple replacement level, the total population shrinks. At first, that might feel like more space and resources per person, which seems good. But pretty quickly you start hitting the point where there are too few workers to maintain complex systems, too few reactor techs, too few doctors, too few teachers, too few engineers. On the other hand, if birth rates spike for a while, you get overcrowding. Life support, farms and living space were designed for a certain headcount. Overshoot that by 20, 30, 50%. And suddenly you're stressing your food production, your air systems and your housing. It doesn't take long for that to create tension and risk. On Earth, we've seen how fast fertility can swing. Some countries went from large families to near zero growth in just a few decades, driven by economics, culture, and education, not biology. On a ship, similar swings could happen, and you don't have another region to migrate to if one area becomes crowded. You just have the ship. Given those risks, you reach for technology as a buffer. Can modern genetics tech buy you extra safety in a small, closed population? We already use genetic screening today to identify carriers of certain diseases before they have children. In vitro fertilization allows embryos to be created and selected outside the body. Gene editing tools, while controversial, offer the potential to remove or correct specific harmful mutations before birth. A generation ship could push this much further. You could launch with frozen sperm and eggs from tens of thousands of donors back on Earth. That frozen gene bank would let you inject new genetic diversity into the population centuries after launch, even if the living founders are long dead. You could use IVF and screening to avoid passing on severe inherited conditions. In extreme cases, you could use gene editing to directly fix known dangerous variants. But that solution comes with its own dependency. Now, your long-term survival doesn't just rely on air systems and farms, it relies on freezers that can stay cold for centuries, on labs that can keep doing IVF and genetic tests, on software that can still interpret DNA data, and on a culture that still accepts and maintains these practices. Your backup against genetic decay is itself another technology stack that can age, fail, or be rejected by future generations. Which brings you to the most disturbing boundary of all. What if the limiting factor for the ship is not physics, not radiation, not materials, but the simple question of whether people keep choosing and managing to have children at all, if social norms, ideology, or long-term stress push birth rates chronically below replacement? The mission has a built-in ending. You can keep all the machines running. You can have perfect reactors, perfect hulls, perfect farms, and perfect robots. But the population graph will still slope down. The last child will eventually be born. That person will grow up surrounded by operational systems, by history, by instructions written for a future that never arrives. Then they will age and die, and the ship will keep flying as an empty automated shell. That sounds extreme, but we already see parts of that pattern on Earth, where some societies are heading towards shrinking populations and aging demographics without an obvious plan for what comes next. A generation ship compresses that risk into a single, sealed environment. Demography becomes a true hard stop. Your starship lasts exactly as long as there are enough healthy, educated, motivated humans on board to keep having viable children and teaching them how to run the ship. And that sets up the next layer of trouble. Even if you solve the genetics, get the numbers right, and keep births and deaths in balance, you're still asking generation after generation to live their entire lives in metal corridors for a goal only their distant descendants will see. How long does a culture like that stay stable before psychology, not physics, pull the plug? Hardware, genetics, radiation, all of that can be modelled. But there's one layer that doesn't follow neat curves: the human mind. You're asking people to live in a closed tube, generation after generation, and never see a real horizon. That's not a normal situation for any species, and we already know how badly much shorter missions can stress people. Look at long deployments in nuclear submarines and in Antarctic stations. Those crews deal with confinement, monotony, strict routines, and almost no contact with the outside world. Studies show higher rates of stress, depression, sleep problems, and conflict, even though the missions are usually just a few months, maybe up to a year, and the crews are heavily screened and trained. On the ISS, astronauts report stress too, but they also report something powerful: the overview effect. They can look out the window, see Earth as a bright living sphere, watch storms and oceans and city lights. That visual link back to home helps many of them cope. Your generation ship crew does not get that. They don't see Earth, ever. They see steel corridors, recycled air, artificial parks under LED suns, maybe a starfield through armoured windows. The psychological anchor that home is down there simply doesn't exist. For the second, third, 10th generation, There is no down there at all. Just in here and out there. And out there is a vacuum that kills you in seconds. Now you might think, we'll pick the most stable, most motivated people. But we've already tried picking highly motivated, stable people for isolation tests that are much shorter than a generation ship, and the cracks still show. Experiments like Mars 500 in Russia and H1Cs in Hawaii locked small groups in simulated habitats for months, in one case up to 520 days. These volunteers were carefully chosen, trained and monitored. Even so, over time, tensions rose. There were mood swings, interpersonal conflicts, drops in performance and periods where communication quality fell. That's in test conditions, with people who know the mission ends on a fixed date, and they get to go home. On a generation ship, entire generations are born into the mission without having any say. Their grandparents or great-grandparents decided to launch. The kids growing up in the corridors inherit that choice. Over decades, that can turn into resentment, apathy, or outright rejection of the mission's goals. Why should we care about some planet 200 years from now when we have problems right here? That question will show up. If you don't have strong cultural answers, the link between daily work and long-term purpose starts to break. That connects to another unavoidable reality. Culture does not stay frozen. It drifts, and that drift can completely rewrite how people on board see their own situation. Languages evolve in just a few centuries. Words change meaning. Accents shift. Entirely new ways of speaking appear. Values and norms can flip in a single generation. Family structures and ideas about work and duty can all change quickly when conditions change. The destination world that fired up the launch generation might be a sacred dream to them. By the 8th generation, it might be a half-remembered myth, a conspiracy theory, or just a boring detail from history class that nobody cares about. Historical data from human diasporas on Earth, migrations to new continents, show that founding cultures can fragment or vanish in under a century. On a ship, that drift happens in a sealed box. There's no outside media, no new cultures arriving, no immigration bringing in new ideas from other places. Everything evolves inside that one bubble. The mission's original purpose isn't guaranteed to survive. It has to be taught, argued, renewed, and maybe reinvented, or it simply dissolves into background noise. You have 1,000 or more people, confined, dependent on shared systems for centuries. That is not a recipe for smooth, unbroken stability. Real states on Earth rarely stay stable for more than a century without major changes. Your generation ship is not some magic exception. Over 300 years, you will see power struggles, ideological movements, likely at least a few attempts at takeover or sabotage. A breakdown in governance doesn't just mean bad headlines, it hits the core systems. If a faction decides maintenance is someone else's problem, if people stop following safety rules, if birth planning policies are ignored or forcibly imposed, you start to get mismatches between population and capacity, gaps in critical roles, neglected inspections. The ship doesn't need a permanent dictatorship to stay on track. In fact, that could be its own failure mode. It needs robust institutions, checks and balances, and a culture that treats maintenance, education, and life support discipline as non-negotiable, regardless of who is in charge. Those institutions have to be strong enough to survive ideology swings and charismatic leaders who want to tear them down. The hardest part is that there is no clear engineering fix for collective burnout. You can't bolt on a morale module and call it done. If the culture on the ship decides, collectively, that the long-term goal is not worth the daily grind, they can just stop doing what keeps the ship alive. Stop training enough reactor techs. Stop enforcing maintenance schedules. Stop teaching the deep technical knowledge that younger generations need. Stop having enough children to keep the population stable. No alarm bell rings when that happens. Systems keep running for a while, coasting on momentum and old habits. Then slowly, quietly, things fail. Skills disappear. And the mission drifts off its original path. Physics doesn't end it. People do. That's why many sober analyses end up at the same place. The main cap on a generation ship's survival is probably not radiation levels, or dust impacts, or even reactor lifetimes. It's sociology. It's whether you can keep a culture stable, motivated, and technically competent across 10 or 20 generations while trapped in a metal world. And even if you manage that, even if your society stays motivated and disciplined, there's another subtle failure mode lurking underneath. All of your procedures, designs, repair methods, and history live in one place: your information systems. So what happens if the ship doesn't go mad, but the software and the knowledge slowly rot instead? Every system on the ship ultimately runs through one bottleneck: computers. They aim the engines, run life support, coordinate robots, track inventories, and hold almost all your knowledge. But computers are not immortal brains. They're some of the most short-lived hardware we build. Look at what we actually see. Voyager's computers are ancient by today's standards, with memory measured in tens of kilobytes, built from 1970s electronics. They've lasted close to 5 decades, with no physical access, mainly because they run slowly, use simple, robust parts, and have conservative designs. Compare that to many modern satellites, which often retire after 15 or 20 years, not because they run out of fuel, but because radiation, thermal cycling, and component aging make their electronics unreliable. On Earth, servers in data centers get replaced every 3 to 10 years. Laptops and phones are old after 5. That's the real replacement rhythm we're used to. A generation ship that aims for 500 years of operation cannot pretend its computers will last like Voyager's, untouched. It has to treat them like perishable organs, constantly swapped, constantly monitored, always in danger of failure. And on top of simple aging, space adds a special kind of failure that slowly chews on your data, whether the hardware is new or not. Random bit flips from radiation. In orbit and deep space, high-energy particles occasionally slam into memory cells and flip a bit from 0 to 1 or 1 to 0. These are called single event upsets. Error-correcting codes can spot and fix many of them by storing extra parity information and checking for inconsistencies. But not all flips are caught in time, and sometimes the upset hits control logic or parts of memory that aren't heavily protected. Over a few months, that's annoying. Over centuries, every piece of running software will be hit by countless random faults. Most will get corrected or cause small crashes that can be recovered from. Some will slip through and alter rarely used data structures, configuration files, or backup code. If your navigation algorithms, life support control code, or industrial controllers aren't built with deep redundancy and self-checking mechanisms, that slow trickle of errors can gradually corrupt the logic that keeps you alive. You might not notice until an emergency hits, and you discover that a critical routine silently changed years ago and was never tested in that state. So you don't just need strong hardware, you need software patterns designed for deep time. Multiple independent implementations of key algorithms, periodic cross-checks between them, automatic self-tests that run continuously in the background, and humans who understand how to audit and repair those systems. That leads right into another problem. Software doesn't just break from radiation. It rots, socially and organizationally. On Earth, we keep it alive with a huge, invisible support network that your ship will not have. Today's codebases rely on patch servers, open source repositories, online forums, corporate support teams, and a constant supply of freshly trained developers. When a bug shows up, someone searches it, finds a discussion, downloads a patch. When a new language or framework appears, thousands of people adopt and improve it together. On a generation ship, you're cut off. There is no internet, no upstream vendor, no external support. The kids growing up on the ship have to learn not just how to use software, but how to maintain operating systems, compilers, build systems, and design tools for centuries in isolation. When a programming language falls out of use, or when the last person who understands an old tool retires or dies, huge parts of your software stack can become effectively frozen. If the compiler for some critical subsystem breaks and nobody knows how to fix or replace it, the code that depends on it becomes untouchable. You can't recompile, you can't modify, you can't safely update. Over time, that creates layers of dark code, parts of the system that still run, but that nobody fully understands. It's the software equivalent of sealed black boxes in the hull. That is dangerous on a timescale of decades, and it's incredibly dangerous on a timescale of centuries. On top of that, even if the code stays understandable, the actual data can slip away because of something very mundane: changing formats and lost hardware interfaces. We've already lost access to some old space mission data on Earth because the tapes exist, but the drives and readers don't. File formats used in the early computer era are hard to read today without emulators and special tools. Even simple media like floppy disks are now awkward to handle because modern hardware no longer supports them directly. Over 500 years, your ship's recording media will have to change multiple times. You might start with solid-state drives, move to some kind of hardened optical storage, then to something else entirely. File formats, compression schemes, encryption methods and interfaces will also evolve. If the crew doesn't actively move all critical information forward, rewriting it into new formats and copying it onto new media every generation, large chunks of knowledge will quietly become unreadable. That doesn't just mean old entertainment files. It can mean repair manuals, manufacturing recipes, calibration data for reactors, medical records, and even basic educational material. So information itself has a lifespan, and someone has to extend it again and again, or it dies. That's why the most important question here isn't how long does a hard drive last? It's how long does a functioning, literate, technically capable culture last? One that understands the value of its library and keeps rewriting it for new tools. You can rebuild a pump from scratch if you still have the design blueprints, the material specs, and the training to interpret them. You can re-engineer a reactor if you still have the physics knowledge and the detailed drawings. You can even reinvent tools if you keep the underlying science and math alive. If you lose that information, or you let it de-evolve into unreadable, corrupted, or obsolete formats, the culture slowly de-technologizes. People still have machines around them, but they become magic artifacts instead of understandable tools. When they break in subtle ways, nobody has the confidence or the documentation to truly fix them. They just patch and pray. That's why the real survival curve of a generation ship might not be set by the durability of its steel or the radiation tolerance of its chips, but by the continuity of its knowledge. If after 500, 800, 1,000 years, you still have a literate population, strong education systems, and a carefully maintained library of civilization that keeps getting updated and translated forward, then your ship can keep going. You can rebuild almost anything from principles. If that breaks, if education slides, if archives rot, if key areas of knowledge are lost, then even with power and air and food, the ship will slowly turn from a controlled machine into a drifting relic, with people living inside systems they no longer truly control. And then, even if you keep your knowledge intact, there is still the outside universe to deal with. You're not flying through a static void. Space itself changes over long timescales, and your path through it is not guaranteed to stay safe. So how do trajectories, navigation errors, and rare but catastrophic cosmic events alter the true upper limit on how long a generation ship can realistically survive? You can get every system on your ship right, but it still has to hit a moving target, across light years, through an environment that never sits still. Space isn't just empty distance. It's a field of tiny forces and rare disasters, and over centuries, those matter. Start with something basic but brutal: pointing the ship. Even inside our own solar system, with short trips, tiny errors add up. Interplanetary probes already need mid-course corrections, or they miss their targets by thousands of kilometers. The burns at launch are never perfect. Thrusters leak a little. Spacecraft outgas trace amounts. And gravity from planets and the sun keeps tugging. Stretch that problem out to 4 light years, about 40 trillion kilometers or 25 trillion miles. A very small initial pointing error, say a microradian, which is a fraction of a degree so tiny you can't see it by eye, will still send you millions of kilometers off course by the time you reach the target system. Enough to fly right past your destination, or into a very different part of that star's environment than you planned for. So your generation ship cannot rely on "we did one perfect burn and now we just coast." You need functional navigation systems, star trackers, gyros, probably pulsar or quasar beacons, and you need propulsion that can run mid-course corrections, not just for years, but for centuries. That means engines that still work in old age, fuel reserves that weren't all spent on the initial acceleration, and computers plus humans who still know how to run the targeting and math correctly after 200 years. On top of navigation drift, There are low probability, high impact events you can't fully predict, supernovae, and gamma ray bursts. In our galaxy, a few supernovae go off every century. Most are far away and harmless. The really dangerous ones, within about 10 light years, are rare on human timescales. Same for gamma ray bursts, which are more directional, but even more intense if you're in the beam. On the scale of a single 500-year journey, the odds that one goes off right next to you are small, but not literally zero. A nearby supernova or a gamma ray burst pointed your way could spike the radiation level by orders of magnitude for a short period, enough to overwhelm your normal shielding. That could mean a wave of acute radiation sickness for anyone in poorly shielded areas, damage to electronics, and long-term cancer risk jumps for survivors. We don't have spacecraft data for this, because we've never had a ship in the wrong place at the wrong time, but astronomical observations tell us how often these events happen, and how far their effects reach. On million-year timescales, they matter. On thousand-year timescales, they are a background risk, small but real. Your design response is simple but heavy. More shielding in core refuges, and a sensor system that would give you any warning that's physically possible, so people can move into the safest zones during a spike. Then there are the solid things in your path that you don't see until you're close. Rogue planets and dense clouds of gas or dust. Surveys have found free-floating planets, objects not bound to any star, wandering through the galaxy. They're dark and hard to detect. The chance that your ship directly collides with one over a few hundred years is extremely small, close to zero in practical terms, because space is vast and the objects are few. But collision isn't the only way they matter. Passing near a massive rogue object could bend your trajectory, or put you through a region with higher dust density. Dense molecular clouds are another hazard. These are regions of gas and dust, with much higher densities than the average interstellar medium. Flying right through a bad one at a significant fraction of light speed could multiply your dust impact rate, ramp up drag heating, and possibly raise your radiation exposure, because charged particles behave differently in those environments. We know from measurements of interstellar extinction how starlight is dimmed and reddened by dust, that the distribution of dust and gas varies hugely with direction. Some paths are relatively clear, others cut through thicker stuff. That means route planning for a generation ship is more like ocean navigation than a straight line in a vacuum. You pick a heading, but you also pick a corridor through the galaxy that avoids known dense regions, the way a sailor avoids storm-heavy waters when possible. Even once you reach a star system, your trajectory problems don't end. If you ever park the ship in orbit around a star or planet for centuries, orbital mechanics starts to bite too. In a simple two-body problem, a ship around a star or a planet follows a stable ellipse forever. But real systems have 3 or more massive bodies, plus small perturbations from others, plus pressure from starlight and stellar winds. Our own solar system is modelled for billions of years, and we know that small changes can slowly pump up eccentricities, trigger resonances, and make some orbits unstable over long timescales. If your generation ship goes into a bound orbit around a planet or star, and you plan to leave it there for centuries or longer, you can't just cut engines and walk away. You need station-keeping fuel and active monitoring. Gravity from moons, other planets, and the star itself will tug on you. Over time, you can drift into riskier paths, maybe crossing debris belts or getting too close to bodies where tidal forces and drag become a problem. So even at destination, the rule holds. Navigation and propulsion never retire. They just change roles from big burns to quiet, constant corrections. Putting this together, most cosmic hazards don't give you a clean, fixed expiration date. They change your odds. On timescales of a few hundred to 1,000 years, your ship is statistically likely to avoid direct catastrophe from supernovae, rogue planet impacts, or ploughing straight through a dense molecular core. Especially if you plan your route with current astronomical data and keep improving that data over the journey. The more dangerous, rare events have characteristic timescales closer to 1 million years and beyond. So for a short 500-year interstellar transfer, cosmic hazards act more like modifiers than hard caps. They raise or lower your risk per century. They might trigger design choices, like extra shielding or conservative speed limits, But they do not say, no ship survives past year 732. Past 1,000,000 years, the picture flips. Galactic weather starts to matter a lot more. The odds of a close supernova, a GRB in the wrong direction, a passage through a nasty dust cloud, or a strong gravitational encounter all go up. On those scales, the universe itself becomes as much of a killer as internal decay. But most serious generation ship concepts don't aim at 1,000,000 years. They aim at hundreds to maybe a few thousand years. In that regime, physics outside the hull sets probabilities, not deadlines. The more decisive limits come from inside: how your systems age, how they fail together, and how much redundancy and margin you build in before launch. So if the galaxy doesn't hand you a simple use by date, you have to find that date in your own design, in the web of components and backups that make up the ship. How many failures can you take before something truly critical snaps? And how long can you keep the whole network of systems inside your reliability envelope before entropy finally wins? By this point, you've seen how everything on a generation ship ages. But there's one more layer you have to face. Nothing fails alone. Real systems die in chains, and your only defense is redundancy and margin, pushed harder than in any machine we've ever built. Start with basic reliability math. Say you have a component with a mean time to failure of 50 years. If you only had one of them in your ship, that might sound fine for a 30-year mission. But a generation ship isn't one component. It's thousands, maybe millions, of components. If you wire 1,000 such parts in series with no backups, meaning that if anyone fails, the whole function stops, your expected system lifetime is way less than 50 years. The more components you stack in a chain, the more likely it is that one of them breaks early and drags everything down. That's why aircraft and spacecraft already use redundancy. They don't rely on one pump, one flight computer, one sensor. They run 2, 3, or more in parallel. If one fails, the others can take over. That's standard for systems where human lives depend on continued operation. Your generation ship has to take that logic and stretch it to the limit. Life support, power, propulsion, navigation, farms, computers. None of these systems can exist as single points of failure. You need multiple independent ways to keep people breathing, watered, fed, and steered. And you need the ability to swap out and repair each path while the others keep running. But simply saying add more copies isn't enough, because redundancy comes with its own costs and its own ways to fail. Airliners often use triple redundant avionics, 3 separate computers running the same algorithms, comparing outputs and voting out a failed unit. For a starship, you might go to 5 or 7 copies for your most critical computers, with diverse hardware and software, so a single bug is less likely to hit them all at once. The price you pay is complexity. Every extra unit has to be powered, cooled, mounted, wired, tested, and maintained. Every connector, every cable, every shared power bus is another possible failure point. If all the redundant units share the same design flaw, or the same weak connector type, a single underlying issue can still take down the whole stack together. We've seen that in real spacecraft. Sometimes it's not the core computer that fails, but the harness that feeds all of them, or a software bug that hits every copy because the same code runs everywhere. Redundancy only truly helps if the failure modes are independent. That means different designs, different implementations, and sometimes even different physical locations on the ship for critical backups. So redundancy is necessary, but it has to be smart redundancy, not just more of the same box. And even with smart redundancy, you have to think about how the ship behaves as capacity slowly drops. Do you get a slow fade or a sudden cliff? Good systems fail gently. They have extra capacity at the start. So when individual parts age and die, performance degrades, but life goes on. Take oxygen generation as an example. You might design the ship with 120% of the oxygen production you actually need in normal operation. That way, when some units age and your total capacity drops to 90% of original, you're still comfortably at 100% of demand. The ISS already follows this philosophy. Its life support has generous margins and multiple ways to do key jobs like CO2, removal and oxygen supply. If one path fails, the station doesn't instantly become uninhabitable. Your ship has to apply this thinking not just to air, but to everything. Power generation, water recycling, habitat volume, food production, computation, communications. At launch, you want clear, measurable excess everywhere, so that when aging chips away, you don't cross a hard threshold too soon. The opposite case is sudden death. 1 or 2 failures drop you straight from fine to catastrophic. A single overload trips a breaker. That breaker shuts down a bus. That kills cooling to a reactor. That triggers an emergency shutdown. And suddenly half the ship is dark. Avoiding that is all about designing systems to fail in stages, not all at once. But even if you build in soft failure modes and redundancy, the sheer complexity of a generation ship means you're always living with the risk of cascading failures. On Earth, power grid blackouts often start with one line tripping, which overloads others, which then trip, and the whole region goes dark. Complex systems like airplanes or chemical plants show similar patterns. A small valve sticks, pressure rises, a relief system triggers, but then some other safeguard was misconfigured, and what should have been a minor event turns into a major incident. A generation ship is likely the most complex single machine humanity will ever build up to that point. It's tightly coupled. Farms depend on power and water. Water systems depend on pumps and filters. Pumps depend on power and control, electronics. Electronics depend on cooling and clean power. Cooling depends on radiators and fluid loops, and on. Draw the failure graph of all those interconnections, and you get a huge web. That means there are many possible chains where one failure in a small subsystem sets off stress in others. Over centuries, unless you are extremely careful, rare combinations will occur. A valve fails on the same day a sensor is offline for maintenance. At the same time, a software update has temporarily disabled a backup path somewhere else. The only way to live with that is to assume cascades will be attempted by reality, and then design layers of defense. Alarms that flag odd behavior before a full trip. Local buffers that can carry loads for a while. Emergency fallback modes that shed non-critical loads while keeping core life support online, and human and AI teams trained specifically to hunt for and break possible cascade paths. When you step back and look at the whole ship as one giant network of components, each with its own failure curve, the idea of a single expiration date stops making sense. Instead, you get a probability curve. Engineers can design individual parts with very long mean times to failure and can plan redundancy in ways that make catastrophic failures extremely rare on the timescales they care about. For a starship, you push that thinking far beyond what we do for cars or planes. You add redundancy, generous margins, constant oversight, and powerful repair capacity. But every year that passes, entropy eats into your margin. Redundant units age together. Spare parts get used up. Software complexity creeps up as you patch and modify. Inspections miss a few early cracks. Education quality might slip in one generation, and maintenance discipline falters. If you model the whole vessel as a network of thousands of interdependent systems, you don't get a fixed best before year. You get a rising probability per century that some combination of failures will overwhelm your defenses faster than you can react. Good design, plus strong culture and strong maintenance, pushes that risk curve far out. Maybe the chance of mission-ending failure stays very low for the first few hundred years. Bad design, weak redundancy, thin margins, or decaying institutions can make that curve spike much earlier, maybe by year 80 or 100. So when you finally ask, how long could a generation ship really survive? The honest answer is not a specific number. It's a range shaped by this rising risk curve. And that's where all the threads come together. Materials, radiation, dust, power, biosphere, population, culture, information. Put them all into one picture, and you can start to say what's clearly possible, what's barely plausible, and what crosses the line into fantasy. So where does all this leave you when you finally force the question, how long could a real generation ship actually stay alive before everything we've talked about overwhelms it? For about 100 years, the answer looks surprisingly solid. With tech that's not far beyond what we have now, you can outline a mission that is hard, but clearly inside the realm of engineering, not fantasy. Thick radiation shielding around living zones, maybe a couple of meters of water-equivalent mass. Rotating habitats a few hundred meters in radius to give roughly 1 G. Fission reactors sized in the tens to hundreds of megawatts, with planned refits. Farms covering a few square kilometers in stacked hydroponics. An industrial base that can recycle metals and plastics and 3D print most spare parts. Keep the population around 1,000, build in generous redundancy, and design your culture around maintenance and technical training. And a century in deep space is tough but plausible. That already covers several human generations. If you can cruise at 0.05 to 0.1 times the speed of light, that's enough to reach the very nearest stars in 50 to 100 years, including acceleration and braking. So on the 100-year horizon, the main barriers are will and money, not raw physics. But push that to 500 years, and the nature of the problem changes completely. Now you're not testing one machine, you're testing a whole civilization trapped inside its own hardware. Over half a millennium, your reactors get rebuilt several times. Computers are replaced dozens of times. Rotating rings get major structural surgery more than once. Your biosphere goes through countless tweaks, crop changes, disease outbreaks, and rebalancings. Your population turns over 15 to 20 times. Languages drift. Institutions rise and fall. Nothing in our spaceflight record touches this regime. We have no 500-year machines, no 500-year controlled ecosystems, no 500-year stable systems to point at. But if you zoom out from rockets and look at Earth, you do see stone buildings that lasted many centuries, simple technologies like metalworking that survived culture changes, and societies that stayed broadly coherent over hundreds of years. So a 500-year generation ship isn't obviously impossible. It just requires you to launch not a vehicle, but a self-sufficient, self-correcting mini-civilization. You need schools that constantly produce new engineers, doctors and farmers. You need governance systems that survive power struggles. You need archives that keep their data readable. If you miss on any of those, your chance of making it to year 500 drops fast. Now stretch your ambition to 1,000 to 5,000 years, and you are stepping onto the edge of plausibility. Every slow process we talked about gets many chances to go wrong. Material creep has had 1,000 years to bend structural members. Radiation and dust have eaten away at shields and outer hulls. Your biosphere has gone through countless small disturbances, each one a chance for a slow drift in nutrients, microbes, or genetics. Demographic patterns have had entire cycles of boom and bust. Cultures have had time to split, merge, and forget their origins more than once. Software and data have gone through so many migrations that only the most robust and curated knowledge survives. On Earth, complete civilizations have risen from nothing, expanded, and then vanished or transformed beyond recognition in less than 1,000 years. Languages from a millennium ago are often unrecognizable to modern speakers. Expecting a shipboard culture to stay tightly mission-focused and technically competent for 3,000 to 5,000 years is a huge ask. On the hardware side, if your industrial base stays intact, there is no clear reason you couldn't keep replacing reactors, rebuilding rings, and refreshing hull segments for thousands of years. Physics doesn't stop you. The giant unknown is whether your social and informational systems can keep up. Will people in year 3000 still care enough and know enough to rebuild a reactor from scratch if they have to? Jump from thousands of years to 1,000,000 years, and you've crossed into a different universe of problems. At that point, a single ship that just keeps going in one piece is almost certainly fantasy. Over 1,000,000 years, galactic conditions around you change. Stars move, spiral, arms shift. Gas and dust distributions evolve. The odds of a dangerous supernova happening near your path, or a gamma-ray burst lighting up a bad region of sky, start to become significant. Even if you avoid those, cumulative radiation damage to electronics, slow contamination of structures by long-lived isotopes, and biosphere evolution inside your hull would distort the original design beyond recognition. Materials that looked stable on 500-year scales might creep, crack, or diffuse in unexpected ways on million-year scales. Entire sections of the ship might get abandoned and rebuilt elsewhere. The population might speciate culturally, even biologically, under different selective pressures. On those timescales, about the only realistic concept is not a single, unbroken ship, but a chain of self-rebuilding, or self-replicating craft. They would hop from star system to star system, mining new materials, building new hulls and engines, and effectively rebooting themselves every few thousand years. That's no longer one generation ship, it's a migrating technological species. So when you strip away the science fiction and force a real answer, you don't get a single magic number. You get a rule. The ship lives exactly as long as you can keep fixing, rebuilding, and learning. Physics lays down conditions, not a timer. It says you must have meters of shielding, or radiation wins. You must have rotating habitats, or bones and hearts fail. You must have abundant, maintainable power, or everything shuts down. You must have a fully closed life support and farming loop, or you starve. You must have a planetary scale factory on board, or you run out of parts. You must have strong education and a culture that respects knowledge and maintenance, or your tools become magic relics. Meet those conditions, and a generation ship can plausibly survive for several centuries, maybe push into the low thousands of years. Miss on any one of them, and your real lifespan shrinks, sometimes down to just a few decades. Beyond that, beyond a few millennia, the thing flying through space is no longer just a ship. It's a travelling civilization that constantly replaces its own hardware, rewrites its own software, and retools its own culture. It only beats the universe by becoming as adaptable as the universe is relentless, always rebuilding itself faster than entropy, and time can tear it down. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.